Hello, everyone. Welcome to the short course ACES using Graphcore Intelligence Processing Units held by Texas A&M High Performance Research Computing. I want to make sure, can you guys hear me well? If you can hear me well, can you give me a thumbs up? Okay, great, thank you. My name is Zhenhua He, and I'm an associate research scientist at Texas A&M High Performance Research Computing. My main responsibilities are to introduce new technologies at Texas A&M to the nationwide ACES community, and also train them how to use the new technologies, and also benchmark the new technologies for performance purposes. So Graphcore Intelligence Processing Units, IPU for short, is one of the novel accelerators on the ACES computing cluster. So let's look at it. Okay, this is the outline for today's short course. In the first section, I will be giving a brief introduction to the IPUs. For example, the architecture and the IPU systems on the Tamil ACES platform. We have two different types of IPU systems on ACES. Today, we will be focused on the more advanced one called Bow IPU system. And another one is called Colossus. I will be briefly introduce them a little later as well. In the second section, I'll be demonstrating on ACES how to run models of different frameworks with the ACES IPUs. The frameworks include PyTorch and TensorFlow frameworks. In the third section, I will teach you how to port a Keras MNIST classification model to run IPU. I will introduce several steps. It's a kind of very standardized steps. So you can apply these steps to your own Keras model. So we hope that you can run your own model on the IPUs as well. In the last section, section 4, I'll be teaching you how to port your PyTorch model to run on the IPU. It's also included several steps, and then you can apply to your own model. And then if we still have time, I have an optional section called model replication. And even we can, for example, you want to distribute your model across multiple IPUs, and then we can run faster, that it can speed up or accelerate your workflow. You can use model replication method or model pipelining method. Pipelining means like dividing your models into smaller blocks, and then you put each block onto different IPUs, and then they can work together and then speed up the whole process. That depends on how much time we have for today. We only have like 2.5 hours, so I guess we will skip some of them, but I hope I can touch everything a little bit, and then you have all these in your mind. When you work on your own model, you can, hey, I can divide in my models and then separate them on different IPUs, and then that can speed up the process. I think for each hour, I would like to give about 5 to 10 minutes break, so everybody can have some water and enjoy a short break. So section 1. Now let's first briefly introduce the computing platform called ACES at Texas A&M University. ACES stands for Accelerating Computing for Emerging Sciences. And it's a accelerated test bed. Actually, we are just finished the test bed phase in August, I believe, and then we are in the transition phase now, but not in fully production phase now. We have a lot of accelerators on ACES, like Graphcore IPU is one of them. So we want the researchers to use all sorts of accelerators to speed up their numerical simulations or AI ML workflows. And also, we provide consulting, technical guidance, and training to our researchers, like the short course today. And also, we provide tutorials in the conference and a workshop. So we want to the users or researchers know how to use the novel technologies on the ACES computing platform. And also we collaborate with other HPC centers and universities on computational and data-enabled research. For example, we collaborate with the TACC, Tax Advanced Computing Center, and the University of Florida, San Diego Supercomputing Center, and many others on some benchmarking projects. And we compare the performance of different hardware accelerators across different platforms. So we also welcome collaboration with you guys. And if you have some research workflow that you want to put on our ACES computing platform, you can let us know. And we will try our best to help you to migrate your workflow to ACES platform, and then we hope that can speed up your research. These are the accelerators on ACES platform. Here in the table, the first one is Graphcore IPU. You can see we have 32 Graphcore IPUs. 16 of them are classless IPUs. They are kind of a previous generation IPUs. Now we have 16-ball IPUs. This is a more advanced version of IPUs. They are a little bit faster. Based on our benchmarking results, we find that it's about like, based on some of the AI machine learning models, we found that the ball IPUs can speed up about like 33% performance gain. And also we have Intel and Bitware FPGAs, Nexus Silicon coprocessors, NEC vector engines. And also we have Intel Optane SSDs that can be addressable as memory with the memory machine. And if you have some workflow that requires a large memory, you can try this as well on the ACES platform. And also we have research scientists who work on this and study the performance of these Intel Optane SSDs as well. You can connect with us and we will let you know our findings. And also we have NVIDIA GPUs. We have 30 NVIDIA H100 GPUs and 4 A30 GPUs. And you can train or do inference with these GPUs. And also we have a lot of Intel PVC GPUs. Their official name is Intel Data Center Max 1100 GPUs. We have 120 of them. And yeah, they are also available for use now. If you want to migrate your workflow to Intel PVC GPUs, you can contact us and we will help you. Next is about the architecture of the Bow IPU processor. As I said, we have 2 different types of IPU system on ACES. The Bow IPU is a more advanced version. It's the world's first wafer-on-wafer chip processor. and it used advanced silicon's 3D stacking technology. So you can see that. And also for these, you can see actually the arithmetic logic units of this processor has been divided into very many smaller units. You can see on this chip, and these small units are called IPU tiles. For each IPU, there are 1,472 independent IPU tiles. Each of them has an IPU core and in-processor memory. So for example, these are the core, and this is the local memory. And these IPU tiles can prepare their own instructions, and so they can do some of their own work. This is kind of a little bit different from GPUs, because GPUs is based on SIMD design, single instruction, multiple data. But for IPU, it's based on MIMD, MIMD design. It's multiple instruction, multiple data design. So this is more flexible, and it can do more fine-grained parallelism on your model. For example, you have a very small batch size, or you want to do some group convolution or normalization. IPU may be better than GPU. And also there are some networking, the links, for example, the IPU links, these IPU links can act as like high-speed channel between the IPUs in your system. This picture is a four bow IPUs. This is one piece of the IPU machine. So for our pod 16 system, we have 4 such machines interconnected to each other. And so we have 4 times 4, that's 16 IPUs. So this is a basic overview about the architecture of a bow IPU. The closest IPUs is a little different. I didn't show it here. It's a previous generation, so we focus on the newer version. This is the Graphcore software stack. Here, I want to mention that besides the driver and for the hardware, we have the Poplar SDK. Poplar is co-designed with the IPUs to facilitate the software development environment on the IPUs for developers. So, for example, it has libraries, communication library, and the engines, graph compilers, and also it supports all sorts of frameworks. For example, the TensorFlow, Keras, PyTorch, Onyx, Hello, Paddle, Hugging Face. So probably most of the frameworks are supported by Graphcore software stack. And also it can support different machine learning applications, whether you do natural language processing, image classification, object detection, large models, or even you do ML-perf benchmark, conditional sparsity, JNNs. These are all supported on the IPU. And also, they have a very user-friendly ecosystem. They provided different tutorials for you to migrate your workflow to the IPUs. They have code examples on their GitHub, and also they have some videos as well. Pretty nice documentation as well. And for some, when you want to look at like the memory usage of the IPU, or you want to do some profiling work, they also have Pulp Vision tools here. Pulp Vision is a visualization tool that can help you analyze the behavior of your model or program on the IPUs. The graph analyzer is can help you analyze like the memory usage by your program. For example, if an operation or a layer, for example, in a convolutional neural network, use the most memory, it will show as a spike on the pop vision graph analyzer. And you can click on it, and it tells you, hey, this layer used the most memory, and you can do some optimization. And also, it has a system analyzer. This is more about the communication between the host and the IPU devices. So you can also probably identify some bottleneck between the host device, your server, and the device, the IPU devices. And also they have debugger, development environment. And I just summarized some of their models. This is just a subset of the models on Graphcore GitHub. I believe they have expanded their models as well. This is I did before, and so they include some vision models, natural language processing models, speech models, GN, multimodal models. And if you want to use run some models on the IPUs, you can first go to their Graphcore GitHub, and they will have the step-by-step guide about how to set up the environment for each model, and including how to download and processing the data set. And they have this is the URL for their GitHub. They call it Graphcore examples. So as a researcher, you may ask, hey, you have all sorts of accelerators on ACES. How can I choose between the different accelerators? For example, AI/ML models, GPUs are pretty standard, and the IPU is seemingly very new and novel, and I need to do some migration work. Does it worth it, or how can I know that? Yeah, we did some benchmark work about the GPUs and IPUs, and you can see on the legend, these are the different systems. So we have been working with the accelerators across different platforms. For example, this is the Greece cluster at Texas A&M High Performance Research Computing, and this is the Lone Star 6 at Tech, and also we have some ACES system. I think it's at San Diego Supercomputing Center. These are the Graphcore, ACES, and also some Graces. So we actually benchmark the performance of IPUs. We use the PyTorch ResNet and the TensorFlow ResNet, and we find that for the IPUs, you can see actually the black bars. We have very similar scaling behavior with other accelerators as well. If we look at this one, the DGX A100, so they have pretty similar scaling behavior. And also, if you look at the X label, you can see we actually compare pairs of IPUs to a single GPU. That is because we considered the price of the IPUs and also the power consumption. We found that two IPUs or a pair of IPUs is pretty similar, like to A100 price wise and power consumption wise. So that's why we compare them with a pair of IPUs. Next is about the TensorFlow ResNet 50, and it's also pretty similar results. We also actually, besides the computer vision model, we also benchmarked with the BERT large models and other models as well in our paper. If you have the link to my slide, you can click on this DOI link, and then you can find our paper, and you can find out what models we used for benchmarking. So actually, because as when I introducing the architecture of IPU, actually IPU is more suitable for small batch size workloads if you want to use a smaller batch size, and also if you have a lot of like group normalization, group convolution, that may be good for fine-grained parallelism. IPU may be a better option. And also, we learned some knowledge when we work on the benchmarks, and you have to be very careful about some of the configurations. For example, for each pod of 16, they have 8 number nodes. If you used, actually, it is recommended for 1 IPU per instance or the host number node. If you use, for example, if you use 16 IPUs, you want to use like 16 number nodes. The processes will be kind of like a swapping among these number nodes that can hurt the performance as well. So check the configuration of your IPU system, and make sure, hey, I only have 8 number nodes. So when I set up some parameters, for example, the instance per IPU, the maximum number is 8, not 16. Of course, it accepts 16, but it just hurt the performance. And also, I talked about the batch size, and we can increase the batch size. And also, we compared compare the performance of IPU with the A100. We found that even at a very small batch size, the IPU can achieve comparable performance to A100 GPUs. So yeah, here it says the similar thing. IPU is more fine-grained parallelism compared to GPUs. Okay, next we will be doing a demo on the ACES. We will be running PyTorch and TensorFlow models on the ACES. So let's see. Hey, we will be using like a monitor to monitor your workloads on the IPU and see, hey, your process is really running on the IPUs. So let's see. First, we will be logging to our ACES portal. You can go to Texas in our website, Tamil HPRC. At the port, and in the portal menu, we have ACES portal access. After you click this, you will get this, and then you will need to authenticate with the access. For if you are access user, you can choose the access CI XC, and then you will need to provide your access ID and your password, and then log in, and then do the dual two-factor authentication. Or another way is you choose your university. For example, for me, I can choose Texas A&M University from the drop-down list, and then I will authenticate through my university system. So that's the similar thing. After that, we will be on the ACES Open On Demand portal. For example, it tells you this is the interface for the ACES On Demand portal. It has different tabs. Okay, I will give you like 1 minute or so to get on this page. Let me check if we have the link to the slides. Okay, I think Josh has posted the link to today's short course slides, and you can open that. For example, here you can find the web page for today's short course, and you can scroll down to the bottom. You can see Graphcore IPU tutorial, and there's a PDF link. So you can download it and save it onto your computer. You can reference it later. So we are here now. So we will do this together from the ACES portal. Let me go to my web page, Tamil HPRC. You can search it. The first one is our web page. Under the portal menu, we have ACES portal access. So I have saved the password and the ID, so it just let me log into the ACES on-demand portal. So let's first explore the ACES Open on-demand portal. You can see actually under Files tab, you have your home directory and a Scratch directory. If you click on, for example, the Scratch directory, you can see your folders and the files here. And also, we have, for example, if you use the file editor on the portal, you can click on the drop-down arrow, and you can click on edit, and you will be able to edit the file. If you are not familiar with the Vim editor or VI editor, you can use the editor of our Open On-Demand portal. It's very convenient too. For example, you can just delete or delete a lot of things like that. And also the next one will be the jobs. And you can check the status of your jobs. For example, pending, now I don't have jobs submitted, so you can check the status of your job. For example, pending, running, completed, or something like that. And also enter jobs, we have a Jonah Composer. Actually, it's in development now. It has some portion working now. For example, if you want to run a PVC job, PVC is the Intel GPU on the ACES platform. For example, I would like to do a PVC test, and you can do an environment. For me, now these environments hasn't been public yet, so I just want to show a demo here. But we do have generic and R. For example, I want to use the Intel TensorFlow container, the container environment. And if you want to upload a file or directory, a folder to here, it will save your files or folder to be here. And then if you need some modules, for example, GCC module or some Python, you can add them here. And you can select the number of cores, number of nodes you want to use. And for example, here, I would like to use maybe Intel PVC GPUs. Total memory, for example, I want to use 100 gigabyte. I wanted to run 1 hour. You can see I would like to, these two are optional. So after that, if you click on preview, magic happens. It will generate a job script, Slurm job script for you. And you type, for example, I want to run 1 hour. Now it's run 1 hour, and your job is named PVC underscore test, and also the memory is set to the memory you typed in the form. And also because this is just an example, so I let it run TensorFlow CIFAR10 classification. I copied the files into the directory. And also I use the TensorFlow container to run this workload. After that, I can click submit. You can see, hey, it submitted a job, and you have a job ID number. So it means like, hey, your job has been successfully running on the cluster now. If you want to check, I don't know if I can see it here. Hey, I can see it here. You can see I have a job ID and it's running in the PVC queue. It's running and it's on ACES cluster. So, of course, you can delete this job. This is just a simple example about our Jonah composer for AI model. And this is a very simple one. We are planning to expand our models in the Jonah composer, and so we can let the users and researchers do more, and they can customize all these steps for their own workflow. Next will be our ACES shell access. So this will open a terminal here, and here I'm on login node 3. ACES has 3 login nodes. Could you please type your login nodes? Like in the prompt, you can see this is your kind of like your user ID. This is the login node number. Can you copy and paste this and let me see what login node you are on now? Next, I would like to show, now we are on the ACES portal, and also we open the terminal. Next will be copying the training materials into your directory. So we are on the ACES login node now. I'm on login node 3. So from the login node, we can SSH into the Poplar, into the IPU system. We call it a Poplar because Poplar is also the name of the Graphcore FDK. So we call it a Poplar. The Poplar 2 has the bold IPUs, the advanced version IPUs. So today we're going to use this IPU system. So in your terminal, do SSH Poplar 2. After that, we can you can change it to your local data directory. We have local data. You can use $user and get into your local data directory, and then make a directory called IPU_labs, and then change the directory to this folder. Next, we'll be copying the example materials to your IPU labs directory. And also, this is the Graphcore examples as I show, and they have the models that can be supported on the IPUs. I prepared some hands-on exercise materials for you as well for today's lab. This will be from my GitHub, and it's called IPU training. You can git clone the repo to your directory as well. So I will give you like about 2 minutes to complete this task in the chat. Okay. To use the IPUs, for example, here we have this is my terminal, and I also need to, because I'm on the login node now, so I also need to SSH to Poplar 2, and also there's a message, hey, this host provides access to the pod 16 containing 16 bold IPUs. So, okay. And next I will be changed to my local data directory. And then change IPU labs. So you can see I have already cloned the Graphcore examples GitHub and my own GitHub repo called IPU training. These two directory will be introduced later. So next, to be able to use the IPUs on the system, we will have to enable the Poplar SDK developed by Graphcore IPU. So what we need do is these files, this enable script has been saved on the system. So we can just source the enable script to activate the Poplar SDK. And actually, these two lines look very similar, but actually they are different. If you look very closely, very carefully, you can see this is a Poplar, this is pop art. Poplar is the Poplar SDK. Pop art is a Poplar advanced runtime. So we will have to include both. if you just include one, they will complain, they will throw you some errors. So, and also our system, we have different versions. Today we are using the Poplar 3.3 and the PopR 3.3. Sometimes if you are accidentally masked the version, for example, if you use 3.4 Poplar, but you still use the 3.3 PopR, that will throw you some weird errors as well. So make sure that you use the matched versions of Poplar and PopR. And also there are some, we will create some environment variables as well. And for the PyTorch and the TensorFlow executables. So these can help you save the compiled executables in the cache, and it will not like compile again and again, and that is very time consuming. So we kind of like we set the directory to be local data user / temp there. So you can just copy and paste these commands into your terminal, and then we can go from there. If you have any errors, you can let us know. So for example, here, I think we can just copy all the commands at once. We can see, okay, by enabling the Poplar and the PopArt, we can actually use some command utilities developed by Graphcore to check the status of the IPUs. So one command is called a GC monitor. We will be using it later as well. So if you type GC-monitor into your terminal and you enter, and you will see the IPUs, the status. Now you can see, hey, no attached processes in this partition. That's great. So nobody is competing resources with us. So today we are going to use the IPUs. And in this table, it's very similar like NVIDIA SMI. If you used a GPU before, it tells you the IPU machine, like the address, the serial number, the IPU machine software version, and the server version. And I think this is the firmware version, and also the type, the ID. If you look at the ID, it starts from 0 to 15. It means like we have 16 IPUs on our system, right? So this is a pod assisting system. And also we have some IPU number. This is local. This is for one IPU machine, so 0, 1, 2, 3, and also the routing as well. So if you want to look at some like, what's not NVIDIA, what's GC stands for Graphcore monitor. And you can actually, it will display the output every 2 seconds. If we have a process running here now, it will show you the process every 2 seconds. So I will just Control C to exit. So any questions here? I did a very easy copy and paste from my file, from my slide. Next, we'll be running a TensorFlow model on the IPU. So what we need to do is to create a virtual environment called venv_tf2. And then we activate the virtual environment. And then we need to install the TensorFlow TensorFlow using this TensorFlow wheel file. So you can just copy and paste as well. So this will create a directory called a venv_tf2 in your IPU labs directory. So So because I have already done the command, so you can see the directory is in my the venv underscore tf2 is in my directory now. So I will give you a minute to run these commands. It might be downloading and installing some dependencies to your environment. So give me a thumbs up when you finish these commands. Or if you encounter any errors, or there might be some breaks, like for this is one line. So if you click on the, let me think. I think I have all these on my GitHub as well. Commands, GitHub IPU training. I hope these all updated. Popular 3.3. Okay, great. I think they are updated. Okay. I will copy and paste my GitHub in the chat. If you have any problems copying the commands from the PDF file, because sometimes I think it gives you errors because of some weird character added to the commands and it breaks or something like that, and you cannot run the commands. So I put the commands in my GitHub as well, and you can just copy from here, for example, copy and paste. That will make your life easier, I think. Okay, I will have my GitHub open as well. Now we are here, the TensorFlow, the environment setup, and then, okay. Now we will run a TensorFlow model on IPU. So after you set up the TensorFlow environment, and you can run the TensorFlow model on IPU. This is called completed demo dash underscore IPU.py. So, for example, here I'll be first. I will active about my environment, and then I will be running this command. So you can see it's running, and it tells you the training epoch, and also it says program ran successfully. It's a very short program, so we just want to show a demo, and if you want to use, yeah, I can see some process on the IPU just now. So if someone else, you can run it on the, yeah. EG is also on the IPU now, and this is a TensorFlow model, and we will quickly running a PyTorch model as well. So you can see it also tells you the temperature, power, like that, and also it tells you which IPU this process is using. So, okay, I just go back, and I will deactivate the environment. This is for the TensorFlow. I was using like a watch GC monitor. Actually, by default, it will display the output every 2 seconds. So you don't have to, if you want to specify a different number other than 2, you can use, for example, watch-n10. It will display the output every 10 seconds. You can see the process and the temperature of the accelerator, the IPU, and the power consumption. So that's pretty similar to NVIDIA SMI. And then next we'll be running a PyTorch model on IPU as well. We will in in Graphcore models, they call they kind of like develop some extensions for PyTorch. They call it a PopTorch. So like when you want to run a PyTorch model, you will have to in Graphcore IPU, we call it a PopTorch model, but it's similar. So next will be very similar to TensorFlow. We will need to set up the PopTorch virtual environment. We will cd change the directory to the IPU labs again, and then we will use the virtual env to create an environment called a PopTorch underscore test, and then we activated the PopTorch testing environment. And similarly, we will need to install the PopTorch by using a wheel file, and it will downloading and installing the dependencies into your environment. So yeah, I have these commands in my GitHub as well. This is the environment. This is the commands. You can run these commands in your terminal. So I think I just need to I'll go back to the IPU labs directory, and then I have the PopTorch test environment directory here as well. Please use the GitHub, the commands on the GitHub, so you can, and also you can follow me on the GitHub. So whenever you want to use the work on the IPU, and you can find the repo. Let me see. Yes, we have RP user u.rp running on the IPU now. Model. Oh, I haven't get the PopTorch model yet. The PopTorch model is in here. The Graphcore examples, GitHub tutorials, simple applications, PyTorch, MNIST. This is a MNIST classification model. So and also you will have to install some other dependencies as well, and then you can run Python MNIST underscore PopTorch. Okay, we have 2 users running on the PopTorch now, on the IPUs now. And also you can see some of the clock speed, temperature, and one is using now, the user.eg is using ID number 1 IPU. So, okay, next, I think it's 11 o'clock now. We finished demoing how to run the PyTorch and TensorFlow models on the IPUs. Next will be like, hey, how can I port some code to IPU? We will show you how to port the TensorFlow code or PyTorch code to IPU. Hello, everyone. Welcome back. I hope my AirPods are still working. So, okay, great. Thank you. Next we will be porting some TensorFlow code to IPU, and so for example, you have a script of TensorFlow, and you have some and it's running on CPU or GPU. How can I migrate this model to IPU? So first thing first, we will need to import the TensorFlow IPU module. At the beginning of your script, you can add this line to your script. For example, from TensorFlow.python import IPU. So we will be using the IPU module in your script. After that, we will have to do something on the dataset, because the Graphcore TensorFlow module, the IPU, they do not work well with a dataset that has a random size. For example, if the dataset, when we do some, for example, the training, we would like to do it in batches, and For example, here, if the size of the data set is not divisible by the batch size, it will be cause a significant performance drop. So that's why we would like to do some preparation work on the data set. And we will create a utility function called make divisible. And it accepts two parameters. One is called number. You can think of this is your data set length, data set size, and also the divisor is your batch size. And we want to make sure that we get a number that is divisible by the batch size. For example, if I have a data set with the size of 101, but I want to use a batch size of 10, I still have a remainder of 1. So I need to get rid of the 1 and make the data set size to be 100, which is divisible by 10. So this is what this utility function does. And if your data set is very large, so the remainder should be just a very small portion. So don't worry about getting rid of a lot of the data. So, and then we can adjust the data set length by using this utility function. For here, we use the load data function to load the MNIST data set. And then we get the training data length by using the square bracket 0. And then we pass the training data set length and also the batch size. We can get a training data length divisible by the batch size. And then we just slicing or pick the data set by using this. So we can just take the first number of training data length images and labels. So we can make it the length of the data set divisible by the batch size. The same operation will be applied to the testing data set as well. So you can see we do the same thing, and so we make sure the data set is divisible by the batch size. If we have a remainder tail in the data set, the TensorFlow module, the Graphcore TensorFlow IPU module, they don't know how to deal with this smaller tail remainder, and so it might cause some performance decrease, and so that's why we do this. We always want to get some performance gain. Next, after we preparing the data set, we will need to add an IPU configuration to use the IPU. So this is from the IPU module config.ipu-config. Here you can see, hey, I can specify the number of IPUs I want to use for my model. For today, for this section, we will be choose 1, and your model will be placed on 1 IPU and using that 1 IPU only. But also, we will introduce model replication later. You can choose more than 1 IPUs, for example, 2, 4, 16, all the IPUs on the system. But for, I guess, we'd better not choose all the 16 IPUs for your own, because we have some other attendees today, right? So if you occupy all the IPUs, we will not be able to for others to use. And then next will be configure IPU system. And also this is just a short list of the options, configuration options. If you want to check the options, you can search Graphcore IPU config options on the website. I think it's very easy to find other options as well, but today we will only introduce these two. Next, we'll be doing the IPU strategy. This is corresponding to the TensorFlow distributed strategy for like distributing your training workload or inference workload across multiple IPUs. I think you guys, if you use GPUs, you want to distribute your training workload or inference workload over across multiple GPUs, right? Similar thing here. We want to use multiple IPU as well, but here, of course, it works with single IPU as well. For the model replication, I will be introducing 2 IPUs. You can use 2 IPUs or 4 IPUs. IPU strategy is a subclass of the TensorFlow distributed strategy. So if your system has 1 or more IPUs, after we created this environment called variable called strategy, we can use another. Next, we'll be creating the variables and keras models within the scope of IPU strategy object. So we will create a strategy.scope context manager and move all the model and code inside it. So here's a hands-on session, and I have prepared a file called MNIST IPU to-do file. It has a lot of like to-dos. I said to-do number 1, to-do number 2. You will need to go back to these slides and then copy and paste these code into the file. You can see it's in the IPU training /keras. So we will be completing the file. This is a incomplete file. So after that, you will be able to run the file. Let me show it in the terminal. Here, I will exit. Where now? And I have the IPU training. Go to the IPU training and go to keras. Here we have some files. Of course, we have the solution file, but I don't encourage you to look at the solution now because I want you to work on the to-do file. MNIST. Oh, this is for replication, so don't look at these 2 files. And let's first do this. So you can see when you open this file, you can see, hey, this is the MNIST script. And first, you will have to import the TensorFlow IPU module. Write your code below. Can you guys see my screen well? If not, I will make the font size a little bit bigger. If you are not familiar with Vim, I can briefly introduce it. And use Vim, your file, and it will open this. Open the file, and then if you want to edit the file, you can click I, and then it will say insert. Now we can do the we can write the code now. For example, from TensorFlow.python import IPU, right? This is our first thing, right? So from TensorFlow.python import IPU. This is the first step. And then you will go to the next step. For example, here, you will see another to-do. Step 2, write a utility function which computes the largest number, no larger than the given number, which is divisible by a given divisor. Actually, I have given you the utility function on the slides, and you can copy and paste it here. But I just want you to familiarize the workflow, this how to change a TensorFlow keras model to run IPU. So we have several steps, maybe 5, 2, 3, 4, 5, and 6. We have 6 steps in total, and you can work on this. I will give you about like 15 minutes, maybe 13 minutes before 11:30. And if you have any questions, you can message me in the chat, or you can start working on your on this file now. After that, we will be continuing about migrating PyTorch model to IPU. Okay, Ren asked about, did I mute myself? Okay, about the last to do, number 6. So let me go back to the slides. Am I here? Yes. The last to do, number 6, is actually corresponding to the number 5 on the slides. So because in number 4, we have specified the IPU strategy by using this. And when we do this, we will have to use create a strategy scope using with Python keyword, and I think it's better to use a I don't want to type in the file now. I'll just show you the MNIST, just to show you the last step here. So in the to-do step 5, corresponding to number 4 in the slides, we have created the IPU strategy. And then for number 6, you will be doing this. Use the Python with strategy.scope, and then put all the model stuff within the scope. And also be careful about the indentation. So these will make sure that all these model and environment variable will be set on the IPU. So if you are not clear about the indentation, if you are not correct about the indentation, then it might give you some error, or the model actually not on the IPU. So that's what I mean. So for the context manager with strategy.scope. Of course, I didn't put all these in the slides, but I want to get you, if you want to change your own code, you will also have the similar thing to make sure the variables that you want, and a model, and a compile, and a training, evaluation on the IPU, you have to wrap all these with the strategy.scope. Good. It's running very fast, or you can use the GC monitor to check your process on the IPU. Okay, this is also a very small model. So, okay, great, thank you. Anyone else running this? For example, here, because you can run this as well. This is TensorFlow. So virtual env, do not forget to activate your virtual environment. I think I have installed all the required dependencies in the environment. So I will just run the solution file. Okay, I need to go back to the file, IPU labs, IPU training, Keras. So you can see it's running, training. We only train it in 3 epochs, so it's pretty fast. If you want to run in more epochs, like train the model like in 10 epochs or 50 epochs, and you can let it run more. I think it's in the file. here, if you wanted to run more, you can change the epochs here, the model fit. We use the fit function for model training. So you can change these like 30 epochs or 100 epochs. It will be run longer for you to check the process, running process when you use the JC monitor. If it's running very fast, you don't even have time to check that. Okay. I will keep moving because of the time consideration, and I hope everyone is working on this, and don't worry about it if you haven't finished it, because we have the solution file, so you can always compare your work to the solution. If you have any questions, you can let us know. Next will be PyTorch. So porting PyTorch code to IPU, and here, as I mentioned, the PyTorch is kind of like renamed PopTorch in the Graphcore IPU. Actually, it's also they developed a set of extensions for PyTorch, and to run the PyTorch models on IPU. And also they use their own advanced runtime to parallelize the model over multiple IPUs. So they kind of like trying to make their own software ecosystem and to make it work better on the IPUs. So again, first, if you have a PyTorch script, you will have to add some statement in your script as well. Although it's a PopTorch, it's a extension of the PyTorch, we still need to import PopTorch. So that's I use. So this is an easy change, and also the Graphcore also developed their own data loader called a PopTorch data loader class. It's an extension of the Torch utils data loader class. And this will be easier to use their underlying PopR framework. So to handle the like a batching of the data. So so we encourage you to use the PopTorch data loader for training the data loader or testing data loader on IPU. And also, when you build the model, like you build the model, setting up the convolution layers, max pooling layers, the group norm, normalization, the fully connected layers, things like that. One different thing is in the forward function on IPU is that we have to put the loss computation on the IPU as well. So if it's training, we will return X and self.loss X labels. So this will put the loss computation on IPU, so it will be faster. This is one thing different. So you can see this is in the forward function. I have highlighted this with red. Next is prepare training. So we can use PopTorch.options. This will like help you for managing the compilation and execution on the IPU. For example, one thing is about gradient accumulation, like number of batches to accumulate for gradient calculation. For example, I want to after like 4 batches of data, I would like to do the gradient computation and average. You can set it up here in PopTorch.options. Here we just use the default, and we didn't, but I want to introduce you that as well. If you are interested in knowing more about the gradient accumulation because you want to do set up a different number, you can search PopTorch options. They will give you a full list of options that you can do. Here you can see we have some wrappers, a data loader wrapper, and we can just pass the options to it, and also the training data, page size here as well, shuffle, true number of workers. This is for the training data loader. After that, we can train the model. Of course, we specify the optimizer. We also have PyTorch.optim. So for Torch, for IPU, you can use the PyTorch.optimum. This is very small, small code change. And also we use the training model wrapper to accept the model, the options as well here, optimizer. And here we want to train the model in 30 epochs. And here the PyTorch model accept the data and labels. After training, a good practice is to detach the model from the device, so the device can be freed and used for other purposes as well. For example, your other workload. And also this is for save the training model weights. Next is about evaluating the model. So we call it a model.eval, and we use the reference wrapper here. We pass the options. For example, if you specify the gradient accumulation here, this will be used in the inference model. And also we have test data loader, similar thing, and also after inference, we also recommend detaching the model from the device, and then at the end it will just to print out the evaluation accuracy. So this is very similar to TensorFlow, like a step-by-step guide. We have hands-on exercises as well for FashionMNIST, the PyTorch IPU to-do file, and you can work on this. Okay, you can go to your terminal. Of course, first deactivate your TensorFlow environment and go back to the IPU labs, and then change. We can change to the IPU training, and then we can change to the, let me see what we have here. Oh, PyTorch. You can work on this FashionMNIST PyTorch to-do file. So you can use the Vim editor. So you can go to the top of the file and then locate the first step to do. It says, hey, import the PyTorch package. Okay, if you forget about the module name, you have to replace the fix me with the module name. For example, PyTorch. Did I spell the PyTorch name correct? You can, of course, you can go to the slides to check. Hey, PyTorch is spelled like this, and then you save it, and then go to the next step to do. You can read the file, and next to do is, hey, you have to do your, this is step 3. We need to, step to do is to add the loss computation to the forward function. So, right, so we have taught about this in the slides, and you can just return. Okay, I have write the return already. So you just need to return for fix me, and you have to fix x self dot loss and blah blah blah, right? So you will have to do this. So you can go over the slides and identify the places that you need to change, and then change it as fast as you can, or you can copy and paste from the slides as well. Of course, I provide a solution file as well. So you can, if you don't want to do a lot of typing, you can follow the steps and to see to this is a standard workflow, so you can know the workflow, and after this class, you have a general idea about your own code or model. Okay, so you can check this. So for example, you come here and check this, and step 3, set up the PyTorch options. You can go to here, hey, and you can just copy and paste this into the file. And step 4, create data loader, and something like that. So I have maybe a fix me. If you want to check the process, I think the running process on IPU, and you want it to run longer, you can change the epochs here. Okay, it's 11:50 now. Can you guys hear me well? My AirPods just died, and I charged it for a few minutes, and I hope it's working now. Okay, great, thank you. Great job. Ren got it wrong on the IPU. Okay, I don't see. So we can go over the solution file together, I think, for the fashionableist PyTorch. So here you can see first to do is to import the PyTorch package. So you just need to write import PyTorch, and then next to do is we need to include the loss computation in the forward function, right? So this is the forward function, and when it's when it's training, we not just return the x, but the loss as well, self.loss as labels. And this is the second to do. And the third to do is here, set up the PyTorch options. Because for this section, we only use a default, so we didn't specify anything here. If you are interested in knowing more about the gradient accumulation and other options, you can specify, for example, ops dot gradient accumulation, for example, equals 10. You want to specify the number of batches to be 10 for gradient calculation. The next one is step 4, creating a training data loader with a PyTorch ops. This is the exact code on the slide, so you can do that. And the optimizer also we included on the slide as well. So we use the PyTorch.optim SGD optimizer. Step 6 is using all these in the training model wrapper, and it has the model, options, and optimizer. Step 7, it's a best practice. If you don't do this, I guess it doesn't complain, but it's just a good practice for you to, when you finish training the model, you detach the model from the device. I guess if you just comment this line, I guess if we have enough IPUs, and then it's okay. But we always want to free the device for other use. Next to do is wrap the model and options in the inference wrapper. And then this is the testing data loader. Okay, and then detach the model from the device for inference as well. So yeah, I hope you guys can understand the flow. So this is about the PyTorch model change that are needed for a model. Next, let me go to my slide. So it's a bonus section. Actually, it's optional. But I think it's very useful for some users or researchers about model replication, because for the previous two sections, we only use one IPU. That is not very useful. When you want to train a model, and maybe you want to distribute the model across multiple IPUs. If it's just on one IPU, it may not have so much performance gain, right? So I want to introduce model replication a little bit here for TensorFlow Keras. So model replication, let me first explain a little bit. It's like you create some copies of your model, and you place all these copied model, the model copies on multiple IPUs, not just the one IPU, for example, 2 IPUs or 4 IPUs, and they can process different sets of the data, and then they communicate with each other, and then for example, average the gradients. So that will be much faster, right? So if you just use one IPU, for example, it takes maybe, but takes time t, and then if you use 4, then maybe a little greater than t over 4. Why a little greater than t over 4? Because there are some communication as well, but still we can achieve a significant speed up. So for our the script we just changed, we need to add some other code, add some other statements in the code as well, scripts. For example, we need to set the number of IPUs equals here, the number of replicas equals 2. For example, we want to use 2 IPUs. And also for here, when we do preparing the data, we also need for, we also set another parameter called steps per execution. This means like the number of batches processed in each execution. Here we set it to be the training data length divided by the batch size multiplied by number of replicas. So so just how many batches, and then the batches are split among the replicas, like the IPUs. For example, I have 4 IPUs. I want to split all the batches into the 4 IPUs I chose. Or here we choose number 2. For example, I want to split the batches into 2 IPUs. So this IPU will process this part of the data batches, and the other IPU will process the second half of the batches. Training data here, we also make it divisible. We also batch size, not just batch size here now, we also times the number of replicas. You can see for testing as well. So these are simple code change. Here we, when we do the IPU session configuration for the TensorFlow model, here we can actually set the device connection type. We can set it to be on demand, like when the IPU is used, it will be attached. When it's not used, it's not attached. So connection type can be always or on demand. If you choose to be always, the IPU will, the IPUs will be always attached to, but I think maybe on demand is a better option. And then for here, we know that in the first step, we choose the number of IPUs to be 2. So we also need to set auto select IPUs in the IPU config to be 2, right? This is the number of IPU, and then configure the IPU system. These are the more options we have used in this section. So after that, in the compiling of the model, we will have to pass the steps per execution. For example, here we have done the training steps per execution and test steps per execution. this has been calculated by using the training data length and the testing data length. So we will need to pass these to specify the number of batches in each execution. And also, now you can actually try using more IPUs for your model. Previously, we only used one IPU. Now you can try 2 IPUs, 4 IPUs. This is also a to-do file in the Keras folder. We also have a solution file, but you can play with the number of IPUs. But I would strongly suggest you to choose the number based like a 2 to the power of 0, that is 1, 2 to the power of 1, that is 2, and 2 to the power of 2, that's 4. I don't know if 8 works because the architecture of the IPU may not support 8, but a 16 definitely works. So you can try these different numbers. I guess this is also the you can see the model running on more IPUs. Let me first run a model. Keras, change to IPU training, change to Keras. This is the solution file. I think I have, let me check what I have here. So this is the bottom of the file. So you can see here, I choose number of IPUs to be 2. So let me run this with the 2 IPUs, the same model, the MNIST classification model. Do I have to change anything else? Okay. This is the TensorFlow model. So let me run it. I first need to activate the environment, and then I will run this one. What? It's better to open another. It's better to open another terminal. So to observe the running processes. I'll just before using the GC monitor, we will have to activate the Poplar SDK as well. So that's a little bit tricky here. If I GC monitor, you can see now we don't have any attached processes in the IPU now. But if I run this one, so we know that we choose to be run the model on 2 IPUs, right? So let me go here. Now you can see I'm using the IPU number 0 and IPU number 1 to run the MNIST classification model. Not just one. This is very fast. So you can change the number of epochs to let it run longer. Of course, we would like you to run to complete the to-do file first. This is for model replication. I'll give you like 10 minutes. We will come back at 12:15 and to look at the model replication file together. Okay. If you have finished the file and completing the file and you run it on the IPU system and use more than 1 IPUs, congratulations. And now you know how to replicate models across multiple IPUs, and that can achieve a significant speed up of your program. So this is a very important milestone. I I would like to go to the file and then let's look at the solution together. Let me find what I do here. What do we need to do here? Oh, okay. I didn't put any to do or something. This is just a solution file. So so you can check your check your files with this solution file, and it mainly just the few changes I have showed you in the slides, and you can also try even number 4. I don't know if there's any hard coded. Oh, that's 4. Let me please number 4. Let's try number 4. And also let me go back to this terminal. Let's see if I'm using 4 IPUs. Okay. Oh, that's because it's doing some graph construction. So before it running the model, it will compile the graph. So compiling the graph is very time is a little bit more consuming. So for different IPUs. Now let's see. You can see now I have for the running the model on 4 IPUs. So 0, 1, 2, 3. And of course, you can run it on 16 IPUs. So for imagine that you have a very large model, a large model that can run on different IPUs and processing just a subset of the batches of the data, and that it will significantly speed up your process. Okay, this is the model replication. Actually, now the short course is over, but I still want to teach you a little bit more. Maybe I want to touch that a little bit. But first, let me finish the slides. If you still need help, you can check our FAQ page. And also we have ACES user guide, and that has some user guide on Graphcore IPUs, or you can email questions directly to our help desk email. We have a lot of student workers who watch the email, and they will forward the email to us, and then we can help you from there as well. If you have some quota issue, for example, the file limits is not enough, the space is not enough, you can always request a quota increase from our ACES open demand dashboard. So, and also this is just some information we request from you to identify any errors or stuff so that we can reproduce the problem. Here's the acknowledge page. We would like to acknowledge ASF, access, and faster. And we want to thank the staff and students at the Tamil HPRC. And also this short course is developed for CSAP pilot program, if I remember correctly. And there are some references as well. So you can see some GitHub for the URL for Graphcore examples GitHub. You can copy and paste into your web browser, and you can look at the Keras and PyTorch as well from there. This is the paper we published on benchmarking IPUs. If you are interested in reading the paper, what models we run, you can also read the paper as well. This is all, and also you can take this survey to help us improve our short course as well. You can do this maybe later. I can, for another technology when you want to, for example, we can replicate our models and make multiple copies of models on multiple IPUs. But sometimes your model, if your model is too big, too large, and sometimes we will have to split the model, called pipelining the model onto, like, for example, you have a convolutional neural network and you can split for example, the first few layers onto the first IPU and the next few layers on the second IPU, and then the remaining layers on a third IPU or things like that. And we can do pipelining as well. Here, there's a file in the Graphcore examples in the completed demos. They have a pipelining. This teach you how to dividing your model into several blocks and put these blocks on different IPUs because your model is too big and it cannot be held by one single IPU. This is a method that we will be using. But if your model is small, it can be held by one single IPU. That's also, you can use the model replication. But if your model is very large, you can think about pipelining the model. So I will briefly go over this. So you can see number of replicas. Actually, this is a combination of replication and pipelining. So for example, we have 4 IPUs.
Why we do so you can see, for example, we have 4 IPUs. For example, you want to use 16 IPUs, but we want to split the model onto 2 IPUs. For example, the first half of the model on the first IPU, the second half of the model on a second IPU. But still, we want to have more speed up. We can replicate these onto 2, for example, right? So because we have the model occupying 2 IPUs, we have 4 IPUs here, and then 4 divided by 2 is 2. So we can generate another replica. So on 2 IPUs, that is 4 IPUs. So, and here we also do gradient accumulation. As I said, number of batches we want to in per replica, and then we need to modify a little bit more here. Gradient, it's just like divisible. You have to change these steps per execution. We have introduced this in the slides. And on demand, a number of IPUs, scope. So here you can see we, in the model set pipeline, did I skip something here? Yes. So here, when you define the model, for example, you use these APIs called keras.ipu.pipeline stage. Pipeline, you can just simply thinking about dividing. Okay, dividing the model. For example, these layers on the first IPU, these layers on the second IPU. So you use these APIs to dividing the model. And after that, there are some changes for the steps per execution. And also, let me see if there's any other changes. Here, the gradient steps per replica, you will have to specify this gradient accumulation steps per replica. And a pipeline schedule, you also need to pass this as well. And that should be running the model on 4 IPUs and with the 2 replications. So that's for the condition of your model is being large. It cannot be held by one single IPU. So this is a bonus section as well. And if you want to think about porting your own model and you encounter any errors, you can let us know. You can send us the email, your questions to the email, and we can help you from there. I think I don't have an exercise for pipelining, so I think that's all for today. We can keep in touch even after this class. If you have any questions, please let us know. And if you want to collaborate with us on some benchmarking projects, you can also let us know. Thank you.